The process begins with a hard alloy cutting tool slicing the aluminum to create a raw blank. These blanks are sized to match the specifications of a single wheel. Once cut, the blanks are placed in a furnace where they are heated for 2 hours until they reach approximately 500 degrees Celsius. This controlled heating process softens the aluminum, preparing it for the forging stage without melting it. A rotary forging machine then applies immense pressure, up to 4,000 tons, to the softened aluminum blank. This force reshapes the material into a thin disc while also altering its molecular structure, significantly enhancing the wheel's strength and durability. After forging, the disc is allowed to cool to room temperature before being moved to a cooling machine. Here, the disc is placed onto a central core while large rollers descend onto it. This process, akin to pottery shaping, gradually forms the aluminum into the recognizable wheel shape. A cooling liquid, usually used to reduce friction, is sometimes omitted for demonstration purposes to show how the metal stretches and reshapes under the rollers. In an incredibly short span of just 45 seconds, the flat aluminum disc is transformed into a 40 centimeters high wheel. Following the shaping process, the wheel rims are reheated to 530 degrees Celsius in another furnace. This step further strengthens the aluminum and refines its molecular composition. Immediately after heating, the wheels undergo a rapid quenching process in cold water. This sudden cooling locks in the new molecular structure, making the wheels even more durable and resistant to wear. Once the wheels have been hardened, they move on to the machining stage where computer-controlled blades cut precise contours into the rims. A small milling machine carves out the spoke design, not only adding aesthetic value but also improving functionality. The open spaces in the spoke design facilitate better airflow, which helps cool the brakes during operation. Additionally, further precision cutting is performed to create bolt holes, which are necessary for securely attaching the wheel to the vehicle. Each wheel rim undergoes a rigorous inspection to ensure it meets the highest quality standards. Sensors measure various angles and check for any imperfections. Even the slightest irregularity could lead to uneven tire wear or compromise vehicle safety. Only wheels that pass these strict quality checks proceed to the final stage. If a wheel meets all standards, it is polished to a brilliant shine, enhancing both its appearance and resistance to corrosion. Once polished, the wheels are ready for use, ensuring reliability, safety, and a sleek finish for automobiles. At GMP, the production of alloy wheels is a meticulous process that blends expert craftsmanship with cutting-edge technology. Our commitment to precision and innovation allows us to produce 1,200 wheels per day while maintaining the highest standards of quality and efficiency. The manufacturing process begins in our 3 dedicated casting areas where molten metal is carefully shaped into wheel forms. Advanced casting techniques ensure durability and structural integrity, laying the foundation for a high-performance alloy wheel. Once cast, the wheels move through 10 specialized product stations, each playing a crucial role in refining and perfecting the final product. These stations encompass machining, heat treatment, surface finishing, and rigorous quality inspections, ensuring that every wheel meets our exacting standards. By integrating lean manufacturing principles, we optimize efficiency, reduce waste, and enhance productivity. Our 15-plus years of experience in alloy wheel production, coupled with continuous investment in the latest technology, has positioned us as a global leader in the industry. Through a combination of state-of-the-art machinery and skilled expertise, we have mastered the art of crafting uniquely designed alloy wheels that are both aesthetically striking and technically superior. Tire recycling is a critical process in waste management, helping to reduce environmental pollution and maximize resource recovery. One of the most efficient ways to handle used tires is through tire baling, a method that compresses multiple tires into dense, compact bales. The REC 7242 terabyte tire baler is a powerful hydraulic baler specifically designed for this purpose, offering an efficient and effective solution for recycling facilities, landfills, and waste management companies. The REC 7242 terabytes is capable of baling 91 mixed tires into a single dense 1,838 pounds bale, which measures approximately 72 in long, 40 in wide, and 44 in high. The compact size of these bales makes storage, transportation, and further processing much easier and cost-effective. Space efficiency. By compressing loose tires into compact bales, the baler significantly reduces the storage space required. This makes it easier for recycling facilities to manage inventory and transport tires for further processing. Cost savings: tire bales reduce transportation costs as more tires can be transported at once compared to loose or shredded tires. This improves overall logistics and reduces fuel consumption. Environmental impact: tire baling minimizes landfill waste and supports sustainable recycling practices. Properly baled tires are easier to process into rubberized asphalt, playground surfaces, and other recycled materials. Heavy-duty construction: the REC 7242 TBT is built with industrial-grade hydraulic components, ensuring long-lasting performance and reliability even under heavy workloads. Ease of use: the machine is user-friendly and designed for efficient operation. With straightforward controls, workers can easily load and compress tires, streamlining the recycling process. Baled tires produced by the REC 7242 TB can be used in a variety of applications including recycling facilities, processed into crumb rubber for use in roads, playgrounds, and athletic tracks. Landfill construction, used as alternative daily cover or structural fill. Erosion control, applied in civil engineering projects to stabilize slopes and shorelines. Energy recovery, used as tire-derived fuel, TDF, for industrial kilns and power plants. The process of manufacturing giant car tires from natural rubber involves several stages, from sourcing raw materials to shaping, curing, and quality testing. The process begins with harvesting latex, the liquid form of natural rubber, from rubber trees. Workers tap the trees by making incisions into the bark, allowing the latex to flow into collecting containers. The latex is then processed to separate rubber from water and impurities. This is usually done through coagulation, where an acid, often formic or acetic, is added to solidify the rubber. After the latex from the rubber tree is coagulated using acids such as formic or acetic acid, the solidified rubber is separated from the liquid portion. This coagulated rubber, often referred to as crumb rubber at this stage, undergoes a washing process to remove residual impurities, excess acid, and any remaining traces of water or natural contaminants like dirt or plant matter. The coagulated rubber is first broken down into smaller pieces or crumbs to facilitate effective cleaning. These crumbs are then washed in large tanks filled with water. Mechanical agitators or paddles stir the rubber, ensuring that all particles are thoroughly cleaned. During this process, multiple rinses may be applied, and the water used is sometimes treated to maintain the desired pH and cleanliness. Washing is crucial because any residual impurities or unremoved chemicals can negatively affect the quality of the final rubber product. For instance, if acids remain in the rubber, they can interfere with later stages of processing such as vulcanization and may weaken the material's overall performance. Once the washing is complete, the rubber is then passed through rollers to squeeze out excess water. After the coagulated rubber is washed and excess water is removed, the rubber is pressed into panels or sheets using heavy rollers. These rollers, often part of a milling machine, compress the rubber into uniform thicknesses, typically between 2 to 5 mm depending on the desired end use. The rubber is fed between the rollers, which apply pressure to flatten and shape it into continuous panels. Once pressed, the rubber panels are hung or laid out to dry fully, either naturally in air or in heated drying chambers. Ribbed smoked sheets, RSS, are a specific form of processed natural rubber that has gained prominence in the rubber industry due to their excellent quality and usability in various applications including tire manufacturing. After coagulation and washing, the rubber is shaped into sheets, which are then subjected to a drying process that significantly influences their properties. To create RSS, the rubber sheets are typically hung on wooden or metal racks in a smokehouse. The smoke from burning wood, often a combination of hardwoods, infuses the rubber with additional preservatives and enhances its durability. This smoking process not only helps in drying the rubber but also imparts a characteristic dark brown color and improves the rubber's resistance to environmental degradation such as ozone and UV light. The sheets are ribbed during the pressing stage, creating distinct patterns that facilitate better stacking and handling. The ribs also help in reducing surface area, leading to quicker drying. After sufficient smoking and drying, the RSS is trimmed to a uniform size and rolled into bales for storage and transport. These bales are then supplied to manufacturers who further process the RSS into rubber compounds for various applications, particularly in producing high-performance tires where its elasticity, strength, and resistance are paramount. In the tire manufacturing process, pocket making is a critical stage, particularly in the production of off-the-road (OTR) tires where durability and strength are paramount. The pockets serve as the foundation of the tire structure, holding various plies, layers, and components together. The process begins by assembling the plies in alternating opposite directions. These plies are layers of rubber-coated fabric, typically made of polyester or nylon, which provide the tire strength and flexibility. Between each ply, a thin layer of rubber compound known as the squeegee is applied. This layer acts as an adhesive, bonding the plies together and enhancing the tire's structural integrity. For additional protection, breakers are incorporated into the pockets. These are extra layers of reinforcing material that shield the tire casing from external damage, such as punctures from sharp objects like rocks or nails, which is particularly crucial for OTR tires that face harsh terrains. JK Tyre's OTR products, for example, offer double breaker protection, ensuring that the tire can withstand extreme conditions. Tire building is a crucial and intricate phase in tire manufacturing, where all the component parts come together to form the basic structure of the tire. The tire building process begins with the assembly of the casing, which is the innermost layer of the tire. The casing is built by layering plies, thin sheets of rubber-coated fabric, onto a rotating tire building drum. Each ply is positioned at a specific angle, bias, to provide the necessary strength and flexibility. For OTR tires, these plies are usually made of durable materials such as nylon or polyester, giving the tire added resistance to wear and tear. A thin layer of rubber compound is applied between each ply to bond them together and enhance their structural integrity. The next critical step involves the insertion of the beads, which are steel-reinforced rings placed at the edges of the tire to ensure it fits securely onto the wheel rim. In OTR tires, the flipped beads are designed to withstand immense loads and pressures. The beads must be aligned precisely with the casing, and this alignment is typically achieved with the help of lasers to ensure accuracy. Special side stitches are then applied to fuse the beads with the casing, ensuring a solid and secure connection. Following bead placement, the tread and sidewalls are added. The tread is the outermost layer that makes contact with the ground, and it is made of a specially formulated rubber compound designed for durability, traction, and resistance to abrasion. The sidewalls provide lateral stability and protect the tire from impact and abrasion. For OTR tires, heavy-duty bottom stitches are employed to consolidate the pockets and PES, ensuring all components are tightly bound together during the tire building process. Chafers, protective layers made of rubber and fabric, are added around the beads. These act as insulators, reducing the heat generated during tire operation and protecting the tire from rim damage. Multiple layers of chafers are applied in OTR tires to enhance their heat resistance and durability. Once all the components, casing, beads, tread, sidewalls, and chafers, are assembled, the tire takes shape on the drum. Precise stitching techniques and electronic pressure control ensure that each layer is properly consolidated and aligned. At this point, the product is referred to as a green tire, an uncured tire that will later undergo vulcanization to gain its final strength and resilience. Curing is a vital stage in tire manufacturing where the green tire, an uncured tire composed of assembled layers, undergoes a chemical transformation called vulcanization. This process gives the tire its final strength, flexibility, and durability by cross-linking rubber molecules. During curing, the green tire is placed into a curing press or mold, which is designed to imprint the tread pattern and sidewall markings onto the tire. The mold is closed tightly around the tire, and high-pressure steam or hot water is pumped into an internal bladder within the tire. This bladder expands, pressing the tire against the mold to shape it while simultaneously heating it to initiate vulcanization. The curing process involves heating the tire to temperatures between 140 to 160 degrees Celsius, 284 to 320 degrees Fahrenheit, for a specific duration, typically around 15 to 60 minutes depending on the tire size and type. The heat activates sulfur compounds within the rubber, triggering the vulcanization reaction. This process strengthens the rubber by forming cross-links between the rubber's polymer chains, improving the tire's resilience, elasticity, and resistance to heat and wear. The process begins with tilt casting, a method used for creating the basic structure of alloy wheels. In this process, molten aluminum is poured into a mold via a tilt casting machine. The machine tilts gradually, ensuring an even flow of metal, reducing defects, and improving the structural integrity of the wheels. After the casting process, the wheels undergo an intensive check through X-ray machines. It's a vital step to guarantee the internal integrity of each wheel. The wheels are then subjected to a T6 heat treatment process, where they are heated to a high temperature and then rapidly cooled. Computer numerical control (CNC) machines play a crucial role in the precision machining of alloy wheels. These automated machines follow pre-programmed instructions to accurately cut, shape, and finish the wheels to exact specifications. CNC machining ensures consistency, precision, and high-quality surface finishes. The process involves removing material from the wheel's cast form to achieve the desired design, dimensions, and tolerances. Next, the wheels are tested for any air leakage. This process ensures that the alloy wheel is airtight and fit for its intended purpose. To ensure a smooth ride, the wheels undergo static balancing tests. This test measures any imbalance in the wheel's weight distribution, which could cause vibrations during driving. Once the structural checks are completed, the wheels are subjected to sandblasting. This process involves cleaning the wheel's surface by blasting it with fine particles, removing any impurities and creating a smooth surface for painting and coating. The next step is the application of a base coat through an automatic wet paint line. After the wet paint line, the wheels go through an automatic powder coating process. This adds another layer of protection to the surface of the wheels, making them resistant to corrosion, scratches, and environmental factors. The wheels then go through mirror face machining, a process where the face of the wheel is precision machined with diamond cut tools. This gives the wheels a shiny, mirror-like finish that enhances their aesthetic appeal. To achieve a high-gloss metallic finish, the wheels are subjected to sputter buttering in a chrome machine. This process applies a thin layer of chrome, which adds both protection and a striking appearance to the wheel surface. The final wheels undergo stringent testing in the Quality Control Lab, adhering to global standards such as TÜV and VIA. Dimensional accuracy is critical for ensuring that the wheels fit properly on vehicles. This test subjects the wheels to simulated forces experienced during cornering and driving. Finally, the wheels undergo dynamic radial testing, which simulates real-world driving conditions. This test checks the wheel's ability to endure road impacts and other dynamic forces while maintaining structural integrity. The intensive final visual and appearance control is the last quality inspection step, where each alloy wheel is meticulously examined for surface defects, imperfections, and cosmetic flaws. Trained technicians and automated systems check for scratches, dents, or irregularities, ensuring the wheels meet the highest aesthetic and manufacturing standards before packaging. The control systems of the Prox tire building machine are designed for precision, flexibility, and ease of use. Powered by advanced PLC systems from German companies like Siemens and Beck, they enable automation and smooth operation. Operators can upload and manage up to 50 custom tire building formulas, allowing for quick adjustments tailored to specific tire configurations. The control panel, placed within easy reach, displays real-time specifications and alerts operators if any components are incorrectly set up. This system minimizes errors, maximizes efficiency, and ensures consistent tire quality. The stitching rollers on the Prox tire building machine play a critical role in ensuring the seamless adhesion of multiple layers during tire construction. There are two sets of stitching rollers, one for lower stitching and one for upper stitching, which are essential in bonding the carcass, PES strips, and other materials without trapping air. These rollers apply consistent pressure across the tire's surface to guarantee even adhesion, which is crucial for maintaining the tire's structural integrity and performance over time. Each roller unit is designed to move in multiple directions, typically 3, allowing precise alignment and application of pressure on complex tire geometries, particularly in large radial agricultural tires. This multidirectional capability ensures that every part of the tire surface is properly stitched, especially in curved or hard-to-reach areas. The green tire constructed during the first stage is transferred onto the shaft and disc plates. These plates hold the tire securely in place during the second stage processes. The shaft ensures precise positioning, while the disc plates are responsible for inflating and shaping the carcass, giving the tire its final form. This shaping process is highly automated, ensuring consistency in tire geometry, which is critical for performance, especially in large agricultural tires. The stitching facility plays a pivotal role in this stage. It ensures the bonding of various layers such as the breaker and tread to the carcass. The rollers in the stitching facility move in 3 different directions, providing the flexibility needed to handle different tire sizes and designs. This multidirectional movement ensures that the breaker and tread are evenly stitched onto the carcass without air entrapment, which could compromise the tire's integrity. The facility ensures precision, guaranteeing that all layers are bonded tightly and securely. The breaker server is a key component that feeds breaker layers onto the tire. The server allows for a maximum breaker width of 900 mm, which is suitable for large agricultural tires. The breaker, which provides additional reinforcement and enhances the tire's structural stability, is carefully positioned and rolled onto the carcass by the server. This step is critical in ensuring that the tire can handle heavy loads and resist wear over time. The final step in the second stage involves the strip winder, which applies the tread to the tire. In this process, strips of rubber are wound around the carcass, ensuring a precise and uniform tread application. This method allows for highly customizable tread patterns, which can be tailored to the specific performance needs of agricultural tires. The strip winding process is fully automated, ensuring that the tread is applied consistently and without defects. The second stage of the tire building process on the Prox machine is essential for completing the construction of radial agricultural tires. This stage involves more advanced components and processes that refine and finalize the green tire built in the first stage, ensuring that the final product meets industry standards in terms of durability, performance, and quality.